Hi guys, so I'm out again today, sorry, but we are going to learn a little bit about mechanical advantage and efficiency, and it's super easy, like easiest thing we've done this whole unit. So we'll start out and talk about what mechanical advantage is. So first of all, copy this down. Mechanical advantage is a ratio. It's just, and it compares your forces. Last time we talked about machines, and we talked about machines like a lever here, and how your lever has usually two different ends. We have a lever arm that you might push on or pull on and apply this, what we call an effort force. That's what you do. Then on the other end, that's where the lever does something else. So like it pushes or pulls on your other object. So if this girl is trying to lift this rock here, this is her resistance force, the load she's trying to lift, and she's applying an effort force. And because this lever arm that she's applying the force to is longer, she needs a lesser force, and this shorter distance can apply a greater force to lift this load. So our formula for mechanical advantage is that mechanical advantage is your resistance force, whatever you're trying to lift or whatever you couldn't do by yourself, divided by your effort force, what you're doing. So resistance force is usually the bigger force. That's what you're trying to make happen. And then your effort force is your easier force. The machine makes it easier for you. So it's usually a lower force. That means your mechanical advantage should be a value greater than 1 if your machine makes work doing easier. Now, it doesn't have units, it's a ratio, so you don't even need to remember anything else. Now, let's look at a practice problem. So you apply a force of 200 newtons to push a box up a ramp. The weight of the box here is 500 newtons. What is the mechanical advantage? So first we need to pick out which force is our effort force and which force is the resistance force. So if you apply it, that's going to be your effort force. That's what you do. The resistance force is going to be the force that you can't do by yourself. So when we plug those in to our formula, we have an effort force of 200 newtons and a resistance force of 500 newtons. And then our formula is resistance force divided by effort force. So that means the 500 goes on top, the 200 goes on the bottom, and we end up with a mechanical advantage of 2.5, and there are no units. Now we have one more formula because we know that the length is also going to adjust our force needed. So we've kind of flipped this equation because we've looked at the length of the effort arm over the length of the resistance arm, because your effort arm should be the longer one, the one that you're doing a longer distance for, and the resistance arm should be the one that's a shorter distance, what the machine does to your object. So let's say we have a caveman here, and he's using a lever, like a seesaw, and he's lifting a rock with it. Now that rock is sitting 50 centimeters away from the pivot point, and the caveman applies to the force to the 1.5 meter side, and we want to find the mechanical advantage. Well, first of all, we do need to make sure we have the same units here. So 1.5 meters, 1.5 meters, let's go with that. We could convert that to centimeters if we wanted, but it's probably best just to convert to meters for both of them. So let's use 50 centimeters converted to meters is just going to be 0.5 meters, 0.5. So which one is our effort arm? Well, that's the one that you do, or that the caveman does. So read carefully. The caveman applies the force to this longer side. Usually the bigger number is going to be on top with mechanical advantage. If the bigger number is on top, then your machine gives you an advantage over just doing this without the machine. That's what we generally want. Then the resistance arm is going to be 0.5 centimeters away. So let's look at our solution. We have our effort arm. Now here I've converted to centimeters instead. You can do that. It doesn't really matter. But we have our effort arm, that longer side that the caveman is applying his force to. And we have the resistance arm, the shorter side. And when we plug those into our equation, we get a mechanical advantage of 3. Now, the only other thing we might need to do with this is see how efficient our machine was, because sometimes we lose energy to heat and friction. We know that. We know that frictional forces take away energy from our system. So your efficiency is always going to be this percentage of how much energy we put in did we actually get out of our machine. And you're never going to have a machine that's greater than 100% efficient. So if you're not sure which work is in and which work is output, then make sure your answer is less than 100%. If it's greater, just flip it around, do it the other way. So we have this guy, Kyle, that's exerting a force over a distance of 100 meters. He lifts this box to this height, and we want to know the efficiency of the pulley system. Well, oh my goodness, we don't have work here. Oh wait, but we can calculate it. We can calculate our output work with the force of the weight of the box times the distance it moves and get 500 joules. That's how much energy the box gained. Now, how much did he put in? Well, he put in this force of 50 newtons times a distance of 100 meters, and he put in 5,000 joules. So really, if we only got 500 joules out, and he put 5,000 joules in, he put a lot more energy into the system than it gained. But that's okay. We can just look at this in terms of efficiency. We have his output over the input, and then we'll get a decimal there. You get this 0.1. So then we just multiply it by 100 and stick a percent sign on the end. Now, if you have a calculator that has the percent button, like don't multiply by 100 and then click percent. Just click that percent button and it'll spit out 10%. You don't have to do both. This is just for our work, and if we're doing this in our head, we stick a percent sign on the end. So he has 10% efficiency because you can't get more work out than you put in. You'll always put in more work than you get out. You'll never even have a machine that is 100% efficient. It'll always be just less than that. So make sure you understand, we've just learned what a machine is last class, and now we've just learned mechanical advantage and efficiency, and now we're comparing output work to input work. All right, so that's really all I have for you today. That's all I have with new notes. So what you're going to do, you have this nifty little worksheet with some mechanical advantage problems. You're going to decide which of these you use. If it gives you forces, use the formula with forces. If it gives you distances, use the formula with distances. And you'll complete these really 5 problems. Then on the back, you've got this machine matchup. Now all you're doing is saying, well, which type of machine can I find? You had those 6 simple machines you copied down last class. If you don't have those notes, they're in chapter 5, I think, of your textbook. And you should be able to remember a lever, a pulley, an inclined plane or a ramp, a wheel and axle, a wedge, and a screw. So those were the 6 that we needed to know. Match them up with what's on this sheet. Once you finish that, you're going to look at the information for your test, your practice test, because we have a test next Monday. So I want you to do as much of this as you can get done. If you can't get through the first page front and back, then that's going to be homework. If you're afraid you're going to lose this, don't forget, you can always put your stuff in your folder by the door. That's fine. And I will see you guys on Thursday. All right, bye.